First, is this, maybe I'll just advance. Some apologies. There was a bit of a scheduling snafu. I do have a little side project predicting Hacker News with TensorFlow and Beam, but I don't have that presented today. So apologies for that. But we will talk about Beam and Dataflow, which sounds similar, maybe. And I'll start with kind of just the evolution of distributed data processing. And we'll kind of walk through how we got to where we are today. That'll give some context for Beam and Dataflow. And then it's a discussion about what's still hard about distributed data processing, which maybe gives some motivation for both Beam and Dataflow. Included in that are stragglers, scaling. I think we're also going to talk about streaming operations, like how do you manage a streaming pipeline. And then finally, if a demo cooperates, we may poke around at Beam just a little bit. So if you're looking for more details on Beam, I just want to give a plug for a 4 p.m. session by Eugene Kirpichov. I think I got that right. He's also a collaborator on these slides. So how did we get to where we are today? 2004, there's the kind of seminal MapReduce paper. And that spawns a whole bunch of work inside Google. Colossus, Millwil, Flume. Millwil and Flume are very related to our conversations today. Meanwhile, the same sort of thing happens in open source, actually. Maybe partially influenced by Google, but also on its own accord. So we have Hadoop, of course, and then all the subsequent and related big data ecosystem technologies. And this is, I guess, the position that Google found ourselves maybe in 3 or 4 years ago, as we try to figure out what's next. Do we keep publishing papers, or maybe it's time that we participate in the open source community? Maybe it's time we release products and code instead of just papers. And that was part of the impetus behind Dataflow. And the subsequent Apache contribution, Apache Beam. And then I'm going to jump from here into a bit of the motivation for these two. So, 3 or 4 years ago, what problems were there still left to solve? Okay, so actually there's lots of problems still left to solve. But maybe here's a few that we were eager to tackle within Google. So event time processing. You've heard that a lot this week. I think it's a hot topic in data pipeline communities. Eugene will be tackling this later, I imagine. This is kind of core to Beam. We're not going to talk about it today. But these other three we will. So say I can stand up a streaming pipeline. How do I make changes to it? This thing's live. It's receiving data. It's has correctness promises. The other concerns are more about how I resource pipelines, streaming or batch. How do I handle straggling workers? And can I deploy these in a kind of flexible, auto-scaled way? So starting with streaming operations. If you stood up a streaming pipeline, you've faced this dilemma where you're suddenly like, okay, now I want to improve it, or I want to make a change, or I want to debug. But you can't mess with that thing that's in production because there's a risk of losing data that's already in the pipeline. If you take it down for some time, you'll be missing data during that downtime. There's also, these systems provide like dedupe exactly once processing promises. And if you take that pipeline down, you may compromise those promises. And then finally, this could impact your write pattern. So perhaps you're writing a file every hour out of your streaming pipeline. If you take that down at the half hour and put up a new one, you're going to get half-hour files. You then recombine those files. So how do people tackle this today? So one approach is I do a parallel swap. So I deploy a second updated pipeline, the pipeline I want to move towards, swap traffic over, take down the first one. Otherwise, I can do what you might call a stop and restart. So I stop pulling from my streaming sources, purge or drain my pipeline, stop the current one, start a new one, restart the sources. So this actually doesn't fulfill all our requirements we listed. It's, we do preserve all the data in the pipeline, but we may be missing new data in the case of a stop-start if we can't buffer the source. Our dedupe guarantees are a little unclear. It's possible for records to be pulled twice into the different pipelines. And it's unclear how we would preserve a write pattern, which may not be a big deal. So what do we want? The ideal is maybe an update in place. So what if I could just submit a new job to the cluster with the same name and an update flag, and it just kind of updates in place. So this is what we've been working on at Google, and it works for minor pipeline changes. And it's included in Dataflow today. But we still encourage some of our users to look at parallel swap or stop and restart in the cases of these major pipeline changes. Okay, so that was our first want. Straggling workers. So what if, anybody who's run MapReduce or big data jobs knows that a system is only as fast as its slowest worker, and often those workers can be really slow. So what causes this worker lag? Well, it's either that the machine is unusually slow or that you've given an uneven amount of work. But the uneven amount of work can happen for a variety of reasons. Maybe it's difficult to predict or difficult to distribute the elements. On the other hand, what's maybe more common, elements may have an uneven expense. They may be variably expensive. So I could take in a stream of URLs to videos and then process those videos. And, someone's going to get left behind with a long video to process. So the usual approaches again, we could kind of filter for bad machines. So we run a probe and figure out who's slow and get rid of them. A common one is speculative execution. So worker A finishes, worker B is still going. So worker A just starts doing worker B's job in parallel. And whoever finishes first gets credit for doing worker B work. So this doesn't actually fix the variable work per element. So A and B are still going to both get long videos, and they're still going to run for a long time. The approach that we're looking at is called dynamic, we call it dynamic work rebalancing. We also like to call it liquid sharding, which we think sounds a little cooler. Here, we have to, the high-level ideas make sense. So we just identify where we can split work, who's behind, split it, pass it on to the next worker, and do so, make this handoff in such a way that we get still our exactly once processing standard. So this sounds great, but it's actually a little tricky. The hard part may be how to identify how long a certain item is going to take to work, how to identify where I can split it. These are challenges we've been working through that we can talk more about. But the status is this is actually working. So you can see before and after here. On the left, we've got the common case, straggling workers all over the place. And on the right, we're redistributing those stragglers, excess work to more efficient workers. Earlier, I shared that we're baking these things into Dataflow, but we've also released an open source SDK, Beam. This is where Beam kind of becomes important. For us to do this work, we need a signal from the source as to where we can split. And standard Hadoop sources don't necessarily provide that signal all the time. So within the Beam open source SDK, we provided semantics for sources to report where they're splittable. Okay, so now on to maybe a third concern of ours, which was how do I scale my workers? Maybe some framing on why this is a concern. So in the traditional approach, you have a bunch of machines at your company, and you stand up a data cluster on those machines of some kind. and then you submit jobs to that cluster. This works fine. Until you want to try doing this in the cloud, where things are infinite and ephemeral. At that point, having a standing cluster gets expensive, and it might be cheaper for you to separate compute and storage. But then you have to ask yourself, how do I then dynamically manipulate my cluster to save cost? How do I dynamically move my job? And even if I can do that, add workers as I need them, how do I assign work to those workers? OK, so the common approach is let's most of our data processing frameworks come with some kind of built-in scaling, auto-scaling functionality. In the next stage, I can add workers, and when we partition data for that stage, they'll get new work. But I also still need to resize my cluster. So now maybe I'm relying on my cloud provider to resize my cluster. And it's unclear that these things are necessarily working in concert. And they're probably relying on pretty rudimentary data, like CPU utilization, rather than data available specific to data processing. So what might the ideal approach look like? Perhaps I don't need this job cluster duality. I can just assign a job to an ephemeral cluster. And they're just kind of one thing. To do that, I probably need fast spin-up, spin-down times, because I'm going to spend a lot of time booting up a cluster, tearing it down, booting up a cluster, tearing it down. And then I'm going to also have to, again, get these data processing specific signals that might not be available to me. And then I have to be able to split work on the fly, because I don't want to wait for the next stage. So how are we doing on this? Well, going back to the Beam SDK, so we're baking into the sources and the I/O of the Beam SDK how parallelizable is a source, how much work there is left to do from that source, how much backlog. Those give us some of the data processing signals we need. This is working great in batch. So you can see here a demonstration using both dynamic work rebalancing, no stragglers, as well as autoscaling. So I'm adding workers. And I haven't really explained these charts, so hopefully they make sense. But I've got maybe 10 green lines going at the top, 10 workers, and then I'm adding maybe another 100 over the course of the job, because the job determines that it can parallelize further. On streaming jobs, still early days. So we have working prototypes, working users using this in production, but still not fully baked into Dataflow. What we're really excited about is now we can think in terms of just jobs. So you can submit a job to the Dataflow API. It spins up a cluster relatively fast, accomplishes your work, and automatically tears down the cluster. So I've kind of given you some motivation at the beginning for why some of the things we wanted to tackle with Dataflow and with Beam. Maybe to kind of summarize and put these into greater context. So we have Dataflow represents that product is where we're putting some of these our approaches on dynamic work rebalancing, autoscaling, and streaming ops, the ability to update a job. The Beam SDK is where we're putting things that we think as a community we all need to be collaborating on, which is if we can do great things with having additional input on sources, then we should all work from the same library of sources. We should all benefit from having increased visibility into our sources that allow us to split data and auto-scale. So the Beam SDK is formerly the Dataflow API, but now it's open source, submitted to Apache, currently incubating. Anybody can go and develop a new Beam compatible source, report the backlog, report where it's splittable. Anybody can then write runners to Beam. So currently Beam works on Flink, on Spark, also on Google Cloud Dataflow, as well as a local runner. So I think I've got just a few minutes here. I don't have a full demo for you, but let me show you a little bit what using the Beam SDK might look like. So I've got here, this is fairly small, so let me see if I can go full screen. Setting up a notebook like this is pretty straightforward. All you have to do is go grab the Python SDK from GitHub. As I mentioned on the last slide, Beam is available currently in Java and Python. Here, this is a very rudimentary example where I create a data source, which is just a table of timestamps and some skew information. In Beam, just like any other SDK, you create a directed acyclical graph, a DAG of computation steps. So I've created my pipeline object here, and then I apply a list of transforms to that object. So in this case, my transforms are just read and then write. I'm not actually transforming anything. And then I tell it to execute, and here I get my output, which is a set of timestamps. A more complicated, you can see I'm having a demo error here, but a more complicated pipeline is visible here. So I'm going to read from a source of input files. I apply a flat map. Kind of like a group by key, I do a combine by key. Here I can do some mapping of values. And then once I've got the data in the place I want, I can write it to some, in this case I'm writing to an analytical database, BigQuery, and applying schema. Now, you could run this locally, as we've done here in this notebook, or you could run this in cloud using Dataflow service. There's a fancy monitoring UI where you can see the graph of a pipeline and see some monitoring steps. So jumping back to the deck here, we've addressed some of those issues. We're pretty excited about them in Dataflow, and we're exposing the parts that are relevant to the community in the Beam SDK. Maybe I think we have like 3 minutes for questions.
Regarding your rebalancing, financial workload rebalancing, if you can detect the splittable points from the workload point of view, why don't you schedule with a smaller chunk of work, then your elasticity will be much better.
Yeah. So why don't we just scale up more machines, spread out, like fully parallelize the work.
And probably don't have to schedule as a top round. If you have a degree like that, you anticipate what kind of computation you need. You can even pre-fetch or pre-initiate the compute to save your latency part.
Yeah. So I think it was Airbnb, they released a toolkit called Airflow.
Yeah.
Do you want to contrast what you want presenting today to
Yeah. So, so as I understand it, Airflow is kind of an orchestration and scheduling framework. So it typically relies on other execution environments to actually to do most of the work. One way to think about it, and forgive me, I don't think I fully addressed your dynamic question, but I'll come back to it. I got carried away. So a data processing job might have its own graph of processing steps, but that job itself might live in a larger graph of processing jobs.
Yes.
My understanding of Airflow is that it orchestrates across data processing jobs that may, within themselves, have a graph. So Dataflow could be one processing job within an Airflow graph, as well as Spark job or a database query.
I come from Dataflow is a kind of machine model in the past. You actually need to exist for your data to do the compute. And imagine one has many tasks all running. You want to stay in more fine granularity.
Yeah.
And you really come into this global scheduling part.
Yeah.
So better thing like that.
Yeah, so and then to your dynamic work rebalancing question, we could scale out quickly first. Our concern is that the processing might be inexpensive. We might overscale and spend a lot of time booting up and spinning down.
schedule on demand.
Yeah, so we schedule, so we do a few workers, see how fast we're progressing through those records, and then we do a, which is
Why
kind
it is breakable? Why schedule a big chunk of data?
yeah, and then we scale from there.
Yeah.
Great. I'm out of time. Thanks, everybody.